Today, I'd like to give you a brief overview of basically cosmological collider physics and related signatures. And hopefully, I'll give you some intuition along the way for why these signals look the way they do. Okay, so as we all know, the inhomogeneous distribution of energy density in the universe as seen through CMB, LSS is a very important data set. And this is the simplest explanation or source for these inhomogeneities that we know is the quantum fluctuations of the field that's driving inflation, the inflaton phi, which are then stretched during inflation to macroscopic scales, explaining these large-scale inhomogeneities. Now, this connection is actually more robust because these fluctuations are actually unaffected by the unknown physics in the early universe, at least on large scales. And because of this robustness of this connection, these inhomogeneities or the pattern gives us a very provides a good opportunity to probe physics at the inflationary scale, which can be as high as 10 to the 13 GeV. So currently, we know that these fluctuations are Gaussian to a very good degree, which means that the inflaton, if it has any interactions, they are small. But hopefully with future improvements and future data sets, we might be able to see some non-trivial 3-point or high-point correlation functions, which would then give us information about the interactions, the additional interactions that the inflaton field has. And more particularly, today what I want to talk about is if these interactions are mediated by another heavy particle, then then actually there's a very unique imprint. There is a very unique correlation that gets imprinted in these inhomogeneities if the correlation is mediated by a heavy field. So this is the topic I would like to focus on the rest of the talk. Okay, so let me just first tell you about what the signature looks like. So of course, we'll consider a 3-point correlation function of the inflaton mediated by some field sigma with some spin s. And the correlation has a unique pattern in, if you look at it in the Fourier space, where the 3 momenta should make up a triangle because of a momentum conservation during inflation. And so you have to look at the squeeze limit, which is when 2 of the momenta are much harder than the third one, the soft momentum. And in this squeeze limit of the correlation, there's this specific form that comes out, which basically has which depends on the ratio of the soft momentum to the hard momentum. And the exponent of this correlation has information about the mass of the field that is mediating the interaction. And also turns out that the spin of this particle kind of leads to a specific functional form in terms of this cos theta angle, which is the angle between the soft and the hard momentum. These are basically these are the Legendre polynomials, actually. So basically, what we see is that the intermediate particle actually imprints. You can kind of, if you study this correlation, you can read off the mass and the spin of the particle by studying the squeeze limit and how the correlation changes in the squeeze limit. So just to go a little deeper, let's look at how the correlation looks for a scalar field, for example. So the unique signature actually comes about in this diagram where the momentum that's flowing through the massive field is the soft momentum. And you can kind of, I have just written out its forms for when the mass is lighter than this number and when the mass is much heavier than the inflationary Hubble scale. So in both cases, if the mass is light, we see that it depends on the ratio of this momentum to this fractional power that's given by the mass of the heavy field. And if the mass is heavier than the Hubble scale, then we see that the exponent actually becomes imaginary. which means that if you look at the correlation and change the squeezing of the triangle, you will actually see oscillations in the correlation function. In the first case, actually, you can infer the mass from studying how the correlation changes as a function of squeezing. But in the second case, there is a very unique oscillatory pattern in the correlation function, where the frequency is determined by the mass of this heavy particle. Essentially, what one thing to notice is that these powers that are determined by the mass of the heavy field, these are fractional exponents or imaginary exponents. So these are inherently non-analytic in nature. And what that means is that they cannot be mimicked by any kind of self-interaction of the inflaton field. So if you see something like this in the correlation function, it must come from a particle, a heavy particle that was propagated during inflation. And because of this property, because of this non-analyticity, the signal is very unique, and it can actually help you, it can actually let you directly see a massive particle. And because of this kind of nature of this signal, it was called the cosmological collider. It's basically very similar to seeing a resonance at colliders, but now the particles are produced at the cosmological scale. So I want to give you some intuition for why this signal looks the way it does. And as I said, the non-analyticity of the signal means it indicates that there was a particle that really was propagating during inflation. So I want to give you a little more intuition of how to easily see this kind of form. So let's focus on a massive particle that's much heavier than Hubble and see what's happening. So the kind of core of this signature is basically gravitational particle production. What is happening is that during inflation, you have a time-dependent space-time, and that actually introduces an explicit time dependence in your Hamiltonian. So to see this, if I take a mode function of just a simple massive scalar field, I'll see that it has something like a frequency, but it has explicit time dependence here. So because of this, you can of course explicitly get the solution for this, but what is interesting is to study the early time and late time behavior of the solution of this function, of this equation. So at early times, you can basically get just a positive frequency solution, showing you that at very early times when the modes are highly subhorizon, they're just in the vacuum state, in the ground state. But if you take the late time limit, you will see that in addition to the positive frequency, you develop some negative frequency component, showing you that, which is basically telling you that what your ground state was at early times is no longer the ground state at late times. And in terms of the ground state of late times, the state that you started with looks like a superposition of vacuum plus 2 particle state plus 3 particle state. It's a superposition of actually, in addition to vacuum, there are amplitudes for 2 particle, 4 particle states, etc. So truly, because of this time dependence in the Hamiltonian, you have actually, at late times, you have created particles from the vacuum. And so, so one more thing is that of course, how much particle production happens depends on how fast your Hamiltonian is changing, and that is also related to the amplitude for this negative frequency component. And it turns out that during inflation, of course, the rate of change of Hamiltonian is just set by the Hubble of inflation. So if you wanted to make anything, so if you're making something that is creating some excitation that's order Hubble, then you would expect this beta to be reasonably large. But if you wanted to make something that is much heavier than the inflationary Hubble scale, then you would have to pay the cost. And it actually turns out to be an exponential cost. And the kind of intuitive way to understand it is like the Hawking temperature of the de Sitter background would be proportional to the inflationary Hubble scale. And if you wanted to cause excitation heavier than that, you would pay some kind of Boltzmann cost. This is very analogous to the Boltzmann factor that you have in thermal theory. This will become relevant later, but for now, I want you to remember that basically inflation is leading to particle production. And knowing this, what this the 3-point correlation actually now looks like is you have Hubble, the expansion of the background has actually pair created a set of heavy particles. And then they go off and decay to the inflatons through the interactions, the inflaton fluctuations. And because this massive particle has frequency that is much higher than the inflationary Hubble scale, you can kind of impose energy conservation in the local frame. And you can kind of see that the decay of these heavy particles to inflationary fluctuation should happen when the energy, incoming energy from these heavy particles is the same as the outgoing energy into the inflaton fields, inflaton fluctuations. And what this means is that this kind of imposing this conservation of energy basically fixes the times when these two particles are decaying into inflaton fluctuations. And they're kind of completely fixed by the mass and the momenta that you're looking at in your correlation function. So basically, one can see that these two times are actually happening at a very different time. So what is happening is when these pairs are getting produced, one of them is traveling actually much farther distance before it decays into inflaton fluctuations. And this kind of propagation of this heavy particle, you would expect a factor of something like e to the I m delta t kind of factor to get imprinted on your correlation function in your amplitude. And so basically here in the 3-point correlation function, the e to the I m t gets imprinted, but the time difference, or the time of propagation is completely fixed by these momenta. So if I basically just use these energy conservation equations and like substitute whatever is the time, you see that you reproduce the signature for cosmological collider, which is just the ratio of the momenta to the imaginary power in Im over h. So the takeaway is that the cosmological collider signature is truly coming from kind of particle production and propagation during inflation. So good. So having seen what the signature looks like, let's see what kind of information we can get from this signal. So the first is, of course, the frequency of these oscillations, or the exponent of the correlation function. It gives you the mass in units of inflationary Hubble scale. That's the first part that we saw. You can also, if your intermediate particle has spin, then the correlation function also has a functional form on the angle between the hard and the soft momenta. So at least for integer spins, you can get also the spin of the particle. One can also actually get the decay width of this intermediate particle. So this is the case where the intermediate massive particle, let's say it also has coupling to some other light scalar that's not the inflaton. And this will kind of create another decay channel for this heavy particle. So basically what it does is, in addition to the usual dilution for a heavy particle, which is just this 3/2 factor, you get additional dilution factor on top of the oscillatory feature. And this additional decay kind of tells you about the interaction of massive field to some other light fields that are not inflaton. One can also get the parity of the operator if one studies the 4-point correlation function. And lastly, this cosmological collider signature can also give you information about the nature of inflation itself, whether it is the usual exponential expansion of spacetime that you think, or some alternatives to inflation, such as, for example, ekpyrosis, or some other. So inflation is alternatives, basically, with some different t to the p behavior of the scale function. And actually, let me also elaborate on this point. And you can also see why the oscillatory signature would be able to do this by going back to how it produces the oscillatory signature in the first place. So again, it is basically connected to this e to the im delta t factor. Now, if basically the two decay times tell us what these two so the energy conservation tells us what these two times are. Now, if you have the exponential scale factor, one can basically get kind of an inverse of that function, and you get a logarithmic. You get a oscillations which is logarithmic in the ratio of momenta. But if you have some different function for your scale factor, the inverse function would get reflected again in the form of what is the variable for your oscillations. So basically, if you have a scale factor that just goes as some time to the p power, then you would expect oscillations where the frequency is still set by the mass of the heavy particle, but the functional form for the ratio of momenta kind of tells you what is the nature of inflation. Right? So I think this is probably one of the very few ways in which one can actually distinguish if the kind of inflation or alternatives scenarios that I know of, at least. Okay, so if you remember, I talked about this exponential suppression if you wanted to see masses that are much heavier than the Hubble scale. So the first question one can ask is, okay, so that means what are the targets that are where heavy particles naturally have masses close to the inflationary Hubble scale, right? So there are a few good candidates. The first is the Standard Model itself. In this case, you can imagine the Higgs having coupling to the Ricci scalar such that it actually naturally gets mass of order inflationary Hubble scale. And in this, if the coefficient in the front is negative, you will have electroweak symmetry breaking, and the entire spectrum gets lifted during inflation. So all of these particles, standard model particles as well as Higgs, would naturally have masses of order Hubble, and that's a good target for a cosmological collider signal. Also, even if you don't have the specific coupling, because of the quantum fluctuations, there would be the variance of the Higgs wave would actually not be zero during inflation. And that also gives rise to Hubble's scale mass for the Higgs, and it will still show up in the 3-point correlation function. The second interesting target is supersymmetry. So inflation breaks supersymmetry, and you would naturally expect heavy particles at the Hubble scale. So that's also a good target. And the third one is GUTS. So typically, the GUT scale is higher than the inflationary Hubble scale at typically 10 to the 16 GeV. But you can consider some non-SUSY orbifold GUTs where the scale can be much lower at 10 to the 14 GeV. And this can be within reach of cosmological collider if the inflation actually happened at the highest scale that is allowed by Planck data at 10 to the 13 GeV. So these are all great targets to go for with the cosmological collider signal. But one can ask, can we actually go beyond? Can we also see particles that are much heavier than the inflationary Hubble scale? Essentially, the question is, can we overcome the exponential suppression that you get in your signal for heavy masses? And the answer is actually hidden in why the exponential suppression comes about. So the source of exponential suppression is basically the rate of change of the space-time. The explicit time dependence only gives you energy of order Hubble, and you want to get more energy. So the solution is, if you have any other explicit time dependence in your Hamiltonian with higher frequency, that can inject more energy than the Hubble scale, and that will make particles heavier than Hubble without paying the cost of Boltzmann suppression. And to illustrate this, let me give you a simple example of a scalar field that we had worked out. So it's a complex scalar field. It just has the usual terms, but it has this specific coupling to the inflaton. It's a derivative coupling of inflaton with the current of this complex scalar field. And you also need a little bit of explicit breaking of this of the U1 of the complex scalar. And what this does, it's easy to see what this does if you rotate the field in such a way that all of these terms disappear, and what you get is them actually added to the symmetry breaking term. So of course, this rotation will not, only affects symmetry breaking term, and it shows up in this factor. It's the exponential of e to the minus I phi over lambda. Now, if you break the inflaton field into its vacuum expectation, wave and fluctuations, you see that you get a factor that goes as the velocity of the inflaton field, which is phi dot. And let's see how large it can be. So from the perturbation to impose, if you impose perturbative control, what you see is that this factor, this kind of frequency, can be as large as square root of phi dot or 60 Hubble. So what this kind of coupling does, it actually introduces an explicit time dependence in your Hamiltonian and in all of your interactions of inflaton with the heavy field. And the frequency is also much bigger than just the Hubble scale. It can be as big as 60 Hubble. So this is basically allows you to make particles as heavy as 60 Hubbles. And this is typically referred to as chemical potential mechanism because of its because this coupling basically looks like a chemical potential, how you add chemical potential in your Hamiltonian. So just to give you an idea of how large the signal can be, basically I'm just showing the two cases of complex spin 0 and a similar mechanism for complex spin 1. And basically for different masses and the FNL value. And what I want to show is that the signal or the 3-point correlation can be much larger than you would expect from this exponential suppression. So these are very good targets. So and basically shows that the cosmological collider may not be limited to masses of order Hubble. Another interesting thing is that the correlation function, the oscillation frequency actually changes in these mechanisms. It's not purely the mass of the heavy field, but also gets contribution from the chemical potential. But there are ways to actually infer both from the data, and I'm happy to chat if anyone's interested. Okay, so in this table, basically I want to just convey that the chemical potential mechanism is not just limited to spin 0 or spin 1, but there are generalizations to spin half, spin 2, which are very interesting, and they all have kind of different characteristics. But they basically can be used to go beyond the Hubble scale. For example, with the spin half, it was used to get signals for heavy right-handed neutrinos in the seesaw model. And with the spin 1 chemical potential, you can actually hope to go to guts with higher energy scale, which is like up to 10 to the 15 GeV. Okay, and lastly, I want to point out that there are other ways where, so whatever I talked until now was the quantum production of the heavy particle, but you can also have other ways in which the heavy particle can get imprinted. So especially if it gets excited classically during inflation because of some feature in the potential. In this way, the oscillatory signatures actually appear in the power spectrum as well as in addition to the bispectrum. Also, if you have some time-dependent mass for the heavy field, in which case that there would be some special point during inflation that the mass, the adiabaticity condition will be valid, and you'd produce a lot of these particles. And these appear as hotspots, as Colin was also mentioning in his talk. Okay, so with that, let me just flash the summary and yeah, take any questions. Thank you.
Wonderful, thank you again. Junu.
I have a question about the scenarios. So in this case, is there a range of P where particle production can happen? And how does the exponential suppression Of
Oh,
e
yeah,
to the
yeah.
minus m over h look like for these scenarios?
Yeah, that's a good question. Actually, yeah, good. I didn't get time to mention that, but yeah, in these scenarios, actually, it turns out. So first of all, the range of p's you consider are typically from like -1 to 0, or -1 to 1, I think. But what is different about these scenarios is in inflation, because of gravitational particle production, even if you have exponential suppression, you actually can exploit particle production. But in these scenarios, it turns out that you need some non-Bunch-Davies initial condition to actually see the cosmological collider signal. Yeah. And sorry, what was the other question? And the Boltzmann suppression. Yeah, so the Boltzmann suppression doesn't directly appear because it just depends. So then the signal just depends on what's the amplitude for non-Bunch-Davies.
Choya.
Thanks for the talk. I have a question about the time-dependent mass. Is that the explicit Lorentz breaking mass, or you achieve it through some other coupling to?
This was the last slide?
Yeah, I mean, yes. It's
So the form, the potential that you need for the heavy particle is basically just its bare mass term, and then a term that basically scans as the inflaton rolls. So basically, when phi is some special phi star, you would have a, if you just kind of plot its mass, there will be a dip when phi is at phi star, and at that point, that's kind of the point where adiabaticity is violated maximally, and you would get maximum production.
Oh, okay, sorry. So it's different from Collins' model of having an explicit mass time dependence.
No, it's actually exactly the same, and the time dependence is basically coming from the kind of slow roll of phi. Yeah.
Here you go.
It seems that you need to have ample with the mass for the oscillations.
Sorry, can you say?
I mean, it seems that in order to have this oscillation, you need sort of ample with inflation to be awarded the mass.
So Diego, if you can press your button in front.
Sorry. Okay. So it seems that you need Hubble of the order of the mass to get this oscillation. Just you need some sort of tuning, some on-shell condition. So I was wondering, because if I keep the analogy with collider physics, okay, usually in collider physics what you do is that instead of doing 2 to 1, you do 2 to 2, and you require, some energy on the extra leg, and then you can produce any other particle, even lighter than Hubble, but still having this oscillation. Because you seem to say that if a particle is lighter than Hubble, I will never have oscillations. But you will never have it because of kinematics, essentially.
I see. So you're.
I mean, it's a question, but.
Yeah.
So if I think about the collider, clearly you are tuning square root of S. That is Hubble.
Yeah, I mean,
Can I do a radiative return in inflation with a 4-point function? That's the question.
So you're asking if you can have oscillatory signatures for particles that are actually lighter?
Yeah.
If I just consider, let's say,
4
loops or some...
No, I would say if I require an extra leg, and there I dump, let's say that M is H minus epsilon, I put the extra leg at distance epsilon, and then...
Actually, I mean...
Maybe it's...
I think I'm kind of seeing what you're saying, but it doesn't completely translate because... yeah, I mean, I can see what you're saying, but the thing that when you say that the mass has to be Hubble to see oscillations, okay, maybe I'll talk to you later. But
Okay.